So you will get those back definitely on Monday. Anybody see who? I think the grades are hidden. And it's this great new, unless you can see it. Did you see it move? Canvas has this new great feature where it hides grades. I hate it. And no matter how you turn it off, it turns it back on the second anybody submits anything or does anything. So I don't know why it's doing that, but I guess you'll find out Monday. If you really want to know what you made, you can come see me. Yes. Any quick questions or anything before we get started? I was like proud of myself with a quick turnaround, then I realized I could hand it back. Everybody's having posted solution. Alright, so that was the end of Unit 1. Unit 2 is an entirely new concept. It's a fresh start until this weekend when we start 2.2. But overall, it's a whole new idea. It's the one, if you've ever had anything with calculus or talked about it, it's the concepts that most people remember are based on derivatives. All that's in Unit 2. At first, the first section is to kind of build some intuition of what we're going to talk about. In section 2, we do the formal definition, which includes a limit. And then guess what happens starting in 2.3? You learn all the shortcuts and you don't have to take limits for the rest of the chapter. So it very quickly moves on to a very new concept. Usually, because chapter 2 is more learning to just compute what we call derivatives using shortcuts, a lot of times it's the test people actually do the test on. Right? Unit 1's a little bit strange because it's the concept of a limit and there's a lot of kind of theory behind it. It's not just compute. Chapter 2 is much more of the direction of here's something, compute something. Right? So definitely, chapter 2 is where you can help improve your grade most. One other comment would be, I don't know how public this one is. It's not on the syllabus. But we do plan to use the final exam to replace your lowest test grade if it helps. So in that sense, you still have a blank slate on the board. All right. The one flaw with that policy is people who do well in the first 3 tests suddenly don't take the 4th test. I don't recommend that. Typically, the unit test, like the chapter 1 test you just had, is going to be much more detailed than what is on the final exam for chapter 1. All right, so there is something to be said that the unit tests are a little harder because they're cumulative on one section and not the entire course. All right, any other comments about or questions about anything? We'll talk about more when we get the test back. Okay. All right, so chapter 2. So we covered 2.1 today, and then we start 2.2 on Monday. So because of that, this homework isn't due until I believe it was Sunday night. All right. And because it's short turnaround in class. But all of section 2.1 is to really just introduce one new idea. Okay? So what's the new idea? How can we, before if you wanted to calculate slope, it was always for a line, right? If you want to talk about a line, you can talk about the slope in the y-intercept. When we talked about parabolas or polynomials or any other type of function, trig functions, we never use the word slope again. And it's because we can only talk about slope for lines. So what we're going to do in chapter 2 is take this idea of slope and extend it to things that are not straight lines. Why did we need a line before to talk about slope? What was the formula? Changing y over changing x, rise over run. If your rise over run is always the same number, it means you're always moving the exact same direction, right? That's only true via line. Once your function does something like curve, you talk about rise over run always being the same thing. Here you're going upwards, now you're going downwards. This whole idea of slope needs to be generalized. So in section 2.1, or all of chapter 2, the idea is how do we talk about slope for a general function? Okay. So in order to answer that, first we'll look at a couple intuition ideas. We'll go with the bigger one first. Let's say we have this function, probably a piecewise function. Over here, what would you say the slope is? So anytime I move 1 unit to the right, it looks like it moves 1 unit down. So for all these x coordinates, I would say my slope looks like it's -1. And then what happens over here? Is my slope negative anymore? Suddenly the graph is going up, right? So it must go from a negative number to a positive number. So what do we mean by slope? The idea is pick a point on your graph and draw what would be a parallel line touching that one point. So here, if you draw a parallel line, it's just the line itself, right? Over here, say you're at x equals 0. What would a parallel line look like if it only touched the y, this one point at x0 was? If it only touched the y-intercept, what would happen here? Have to be a horizontal line. If it was tilted in any way, it wouldn't look like it's parallel. So in order to touch here, it looks like I'd have to draw a horizontal line. So we would say the slope of this function is 0 when I plug in x equals 0. If I change my x coordinate, is the slope 0 anymore? No. So our goal is give me some graph or some function f of x. So I have some function f of x. And then based on this, I want to write a new function f prime of x, which tells me the slope of f at the given x value. So f of x is mx plus b. If we have a line, what's f prime of x? What's the slope of a line? Always that coefficient. So here, this function would just be the y-coordinate m, always. What's my slope at any given x value? For this function, my slope is always m. In a line, the slope never changes. What we're saying now is, here's a more interesting function of f. My slope could change at every x coordinate. If it's always changing, that means when I plug in x, I need to output what the slope is. Before, when we talked about lines, did we say what's the slope when x is 3, what's the slope when x is equal 5? We just said what's the slope, right? And it's because it didn't matter what x was, the slope is always that m value. Now we want to talk about things where the slope could continually change. So you have to give me an x coordinate, I look at the graph, and now I figure out what would be the slope of that x coordinate. So we said x equals 0 looks like the slope would be 0. Because I was going to touch here, it'd be horizontal. If I plug in -4, my slope would be -1. If I plug in x equals 2, my slope would be a negative number. Why is it a negative number? You try to draw a horizontal line or a tangent line here to touch this graph, it has to have a negative slope. Bad positive slope is that parallel. So over here it'd be negative. Over here it's negative, but less negative, right? So we can, it actually comes up to a new concept. What's the slope of the slope? We do. We know these slopes. Hey, this is a function. I can now talk about its slope. But the idea is I'm given f. When I put a prime here, it means look at your original function and now tell me the slope at every input. I have a bonus question. Is there any place this graph would not have a defined slope. Okay. X equals -2. What goes wrong at -2? I have a corner. I would call it a corner, I guess. Yeah.
That would just be a zero slope.
Would it? So a tangent line touches the graph and is supposed to be parallel. Is that parallel? If I were to, I could touch the point at one place and this line looks like it would work, right? Same with this line.
It has to be gradually changed.
We actually can't define a slope right here. We'll talk about why in a little bit. It comes back to the definition that we haven't defined yet. But anywhere like this, you can't really pick a slope because from the left, let's say my slope is a negative number. From the right, like -1, not near 0. From the right, I'd say it's this positive number. If something weird happens on the left and the right, can we just glue that together? Can we have multiple slope values at one x coordinate? We're saying this needs to be a function, right? If you have a function, you plug in one number, you get out one number. So I can't say output -1 or this positive number. So instead of making a decision, we just say it's on the top. And that's actually the next slide here. The blue curve would be f prime of x. Does it make sense for x less than -2, my blue curve, if I graph it, is at -1? We said anywhere on this side, this looks like it has slope -1. So if I graph my derivative, my slope function, I'm sitting at -1. And then we said at -2, it goes from this negative value to a positive value for the slope. And we see that here, we just have to jump this continuity. But then we use open circles. We can't pick a single value. And then what do we say the slope should be when I plug in x equals 0? Should be 0, because I have a horizontal tangent line, must be slope 0. And then what happens over here? My slope is negative, but as I move this way, my slope is less negative. So does that kind of, when you see the blue curve, does it match what's happening on the red curve? That's the skill we want to build. Can I look at this red curve and figure out what the blue curve looks like? If I'm given both, can I say why this relates to this? Like, we need to be able to see the two things at the same time. Another one. This is just to give us, so we're calculating, this is bleeding into 2.2 a little bit. 2.1 and 2.2 are really the same section. In 2.2, we just tell you to do this with limits. This would be my tangent line, this one on the top. So if I tell you x is negative, whatever this value is, or if I'm putting on the graph, this little blue line segment looks like it would be tangent. If I check, it has slope roughly -3. At x equals 0, my slope should be 0. If I move over this way, now my graph is moving upwards. If I draw a tangent line, it has positive slope. So if I trace these, it actually calculates my derivative, or my slope values. And you can see over here, my slope must be positive. Over here, my slope must be negative. As I move towards here, my slope is moving towards 0, right? Until I get to right here where my slope has to be 0. Because my graph is turning around, I have this nice, if I drew a tangent line, it'd be horizontal. So we can see that here. The slope is negative, but it's getting less negative, it's 0, now it's positive, getting more positive as I go. Does that make sense with the shape? As I move out this way, it gets steeper and steeper. So my slope must be a bigger and bigger positive number. What about this one? When I graph the slope, is it ever 0?
It is
X equals 0 for that one instance, my slope is actually 0. But then what happens? It quickly starts moving up again. Is my slope ever negative? If I try to draw tangent lines, that one's always pointed upwards. No matter what, it's pointing upwards. When I move over here, it's still pointing upwards. So all those are positive numbers if I find the slope. And yeah, we see that. The slope is always positive, but it is 0 exactly when x is equal to 0 because my curve for that one instance leveled off. And then immediately began moving upwards again. So why we call it the instantaneous rate of change. For that one x value, that one instance it holds. Another way to think about this, some people mention this, it's in the reading and all. If you're driving your car, what is your speedometer telling you? It's always your instantaneous rate of change. It's how fast you're moving. Slope and how fast you're moving, velocity are really the same concept. If you think of position as your f of x, your velocity is f prime of x, it's the slope. How do you find velocity? So say we're measuring position, like I'm driving down the road, I can measure how far I've driven, right? That would be my position, how far have I moved in this one direction. You measure that, say, in miles. What would be your slope? When you do slope, change in y, we're changing x. My y coordinate would be miles. What would be my x coordinate? Time. What do you get when you do distance divided by time? That's like miles per hour, right? Rise over run, in that context, would be distance over time, miles per hour. Now you're getting velocity. So it's almost like tracking your location the whole time. What would f prime look like? Record what's on your speedometer every instance. Is your speedometer changing? Yes, your slope, your velocity is always changing a little bit up and down. All right. What does it mean if your velocity is 0? You wouldn't be moving. It's like you came to a stop. All right. In this one, it's like you came to a stop and then instantly hit the brake or hit the gas. So, the world's fastest stop sign stop. Technically, I lied a little bit. Your speedometer doesn't give you velocity because it doesn't tell you if you're moving backwards. In order to get slope, you have to allow negative numbers. So if you're in reverse, you have to put a negative sign in front of your speedometer. Then it actually works. Otherwise, you only know you're moving forwards. So which function is this, sine or cosine? Sine. Here is most of section 2.5. No, 2.6. What's the slope of sine of x? Cosine of x. It's amazingly simple. There's an amazing relationship there. Would it make sense, let's see it, when I plug in, when I'm here, my slope is positive, right? The amazing fact is it's positive 1. There's no easy way to see that one. What happens here? I turn around. So my slope would be 0. That's exactly when this part is 0. At this angle, cosine would have to be 0. So you end up with this type of relationship. Alright. So slope of sine of x ends up being cosine of x. Slope of cosine of x is negative sine of x. Sine of x would be going this direction, and negative sine starts this way. Well, e to the x. My slope should always be positive because it's always moving upwards. When I go off to the left, my slope is moving towards 0. When I go off to the right, my slope should go up to plus infinity because it keeps bending upwards faster and faster. Here's the most amazing fact. The slope of e to the x is e to the x. It is the only function f of x where f of x and f prime of x are the exact same thing. That's actually section 2.5. But e to the x, why do we care about e to the x? It's the only function that has this property. What if I change it to 2 to the x? Now it doesn't work. Slope of 2 to the x is not 2 to the x. It has to be the number e. That's the only time that actually works out. Although we're not far, it's 2 to the x times natural log of 2. Now you can see the red curves on top of the blue one, or all the points. It's purple. But does it make, that's a little bit beyond where we get the formulas. In this section, we don't know the formulas. The goal is, does the picture of the slope make sense given the original? If I give you this orange curve, is it believable that this is the slope? And usually we look at high-level properties, like the slope should always be positive. If I keep bending upwards, my slope goes to plus infinity. That would make sense with this shape. If I move this way, I'm kind of leveling off as I move to a horizontal asymptote. Horizontal asymptote says I'm close to a horizontal line, right? What's the slope of a horizontal line? 0. So it makes sense my slope is moving towards 0. So how do we find slope? So this is the last thing I want to talk about for big ideas. Then we can do some more examples. We're given f of x, and we want to find the slope. If f of x were a line, we said just pick the coefficient, right? Well, what does this really represent? This would be change in y over change in x, or y over rho. How do you find the rise in a function? Give me 2 points, one here, one here. Say this is point x1, y1. This is the point x2, y2. How do I find the slope? My rise is the change in y, the change in the x direction, or the y coordinates. So y2 minus y1 over the change in my x coordinates, x2 minus x1. Does it matter which point I choose or which 2 points I choose for this? If it's a line, then I could just pick any 2 points on the line, right? And then the slope between them must always be the same thing. How can I carry that over to a general function f? I want to use this same idea where I say start at location x. Or how could I go from here to here? Let's call this point x, this one y. How do you go from here to here? I could say this is my run, right? So what point would this be? X plus some run value h. And then how do I get this distance? I would need to know this y coordinate, right? What would this y coordinate be?
Y plus f of h.
Yeah, how do we get y coordinates in general? I know an x coordinate. So my x coordinate, if I start here at x and I say I want my run to be h, my new x coordinate must be x plus h. I know my old y coordinate. How do I get my new y coordinate? In general, how do you get y coordinates if you know a function? Just plug in? Alright. I don't know what the y value is, but it's, how would I come up with it? Plug into f. This is actually the biggest hurdle in this unit, or really the rest of the course. F tells us y coordinates, f prime tells us slope. If I input x into f, I get a y coordinate. If I input x into f prime, I get a slope value. They're not going to be the same number. But f prime is related to f because it's telling me the slope of my original thing. That's why we don't change it to like letter g or something like that. F prime says this is related to the function f, but it's definitely a new function. The reason I'm kind of harping on that, when you write things, make sure you label it as f, label it as f prime, make sure you don't drop primes or write a bunch of equal signs where you go from f to f prime randomly. Because later in the semester we'll say we need to know the slope, we must plug into f prime, or we need the y coordinate, we must plug into f. If it's not well labeled, you can easily plug into the wrong thing. So our goal was, how can we mimic change in y or change in x? So we're going to say start at the value x, and for my second x coordinate, just move h units away from where it started. So this is my y2, based on my original y coordinate, fx. That tells me rise, right? What would be my run? X plus h minus x, which gives me just an h. So we chose the run. We said move h units. Is this going to give me the right answer? So here's some graph. Let's start here with x. And now I move h units this way. Now I have this point here, right? So when I do this formula, what am I finding? I'm finding the slope of this line. Is that going to be the exact same slope as if I started here? Probably not. So what can I do? But let's see. Here I'd say my slope is a little bit positive. Here it's a little bit too positive, right? I overestimated. How can you get a better estimate? What if I take this to be h? Now I have that as my line. Is that looking like a better value for the slope?
It'll get closer as you.
The purple line, the slope was too big. The red one, the slope's a little bit too big, but it looks closer, right? So what can I do to eventually get to the right answer?
Find a limit.
Yeah, there's a fundamental flaw. Or this is a high-level issue. We only want to know the slope at this one value. When you use lines, how many points did you need to find slope? So I want slope at one point, but I've always needed 2 points to find the slope. So how do we solve that problem? If we want slope, we have to have 2 points. So the idea is pick 2 points, but make your second point a better and better choice.
Because so if this is a 0, it would mean 2 points.
Yeah, if my run were 0, it would make sense, except if I have run at 0, I have 1 point.
Yeah.
So I can't do that. So how do you fudge that?
Well, limits.
Make a limit as h goes to 0. This is the definition of the slope. Why did I need a limit? To find slope, I need 2 points, but I want slope at 1 point. So what is this idea? The idea is pick 2 points, but make your second point so close to this one it becomes indistinguishable. But I need a second one so I can rise over run. in the book and everything, this one was called a secant line, whereas the thing I care about is the tangent line at that one point. So if we go back to this example, why do I not have a slope at -2? Say I'm sitting at -2, and I pick h to be a negative number. I would be finding the slope of these secant lines. What would my slope be? A negative value? -1? What if I'm sitting here and I pick h to be positive? Now my second point is somewhere over here, which means when I try to find the slope, I'm somewhere up there, right? So if I take a limit as h goes to 0 from the left, my value would be -1. If I use a limit from the right, I'm using these values, I would be going to +4. Do I have a limit if I have -1 or +4? My left and right limits don't match, therefore I don't have a limit there, or a value there. There is no limit. In order to have a slope at a tangent line, in order for this whole formula to make sense, I must have a limit. So if my left and right limits don't match, I can't have a slope value. I don't have a derivative value. You derive the slope formula. This holds now for any x value, right? When you take the limit as h goes to 0, eventually you plug in, right? When you plug in, are there any more h's? The only thing that will actually survive are the x's. So this will now, once you can take this limit, when you take a limit, whatever you plug in, this value goes away, right? Like say you have a limit that exists, eventually you plug in, you get the number. Now when you plug in, you get the number corresponding to slope for that one x coordinate. But you can do this for every single x coordinate, which means we can find the slope at any x value. It doesn't matter that my curve it's a curve, it's not a line anymore. All those issues go away. All right? So in order to find the slope of a general function, you have to use limits. This is actually why we do unit 1, just so we can say this in unit 2. And we'll say it for 2 or 3 days, and then we move on. And one short test. All right? So that is how we find slope. It's how we think of it. We're going to use that formula a lot next week. It's the one you just have to memorize. Any questions so far? So this one, that's actually what this is thinking of. I can take h to be much smaller. So like my tangent line is this value. If I pick h to be closer and closer to 0, my secant lines essentially line up with my tangent line. If I pick h negative, it's a little bit under. H positive, it's sitting there. It would say here my slope should be roughly 0, right? So I want to get there. You can see my slope's too far under. As I get closer, degrees, and I'll move this way. It's too far. So we're going to limit h goes to 0. So this is the one that matters. Somewhere like this part of the graph. That one almost looks like a line for that part of the graph, right? The slope isn't changing a whole lot. So you can see I can actually pick a pretty big h value and still have a good estimate. All these are technically secant lines, but they're very close to that one tangent line. How many tangent lines do you have at a point? Just one. So our goal is to pick a bunch of secant lines and then limit that give me just that one answer. One other comment. What happens if I plug in h equals 0 here? It'd be f of x minus f of x over 0. So I get 0 and 0. By definition, this limit will be an indeterminate form. You always have to do more work, factor, cancel, do something else before you can actually find the slope. Why does that one make sense? Because you say h is 0, it means your run is 0. You only have 1 point. You can't talk about rise. You always have to find these and then take the limit after you cancel or do something else when you start doing the work. But you can see it does. As I said, h to 0, this is giving me an answer. I just have to do the work to find the limit. And it's giving meaning to that limit value. Here's another one if you want to graph what the slope looks like. You can just trace along the graph and all the tangent lines. Whereas, like, say I want this tangent line, what can I do? I lock this coordinate, and then I take a secant line by picking a separate coordinate. As my x value gets closer to here, the slope matches, right? Alright, so all that was to build up to our daily problem. Not daily problem. Graph one. What does this say? This says find a function, or sketch the graph of a function whose slope is 0 at 3x coordinates. Do I care what happens at any other x coordinates? Do I know a y coordinate? All these only say f prime, right? If it only says f prime, all I know is slope. I know nothing about y values. So I wrote a couple of these. First one I drew was this. Does this one work? So this notation says when I plug in -3, my slope needs to be 0. So here's x equal -3, my slope is 0. If I plug in, -1, my slope should be 0. So here you see my curve kind of levels off for that second, or that instant. So it has slope 0, so it checks. Does it matter that my slope isn't 0 in between? Does it matter that I drew the y coordinate here? I didn't tell you a y coordinate. It could be anything. I could have made this point up here and drawn it like this. This would still have slope 0 at the point where it turns around. Alright? We're not telling you y coordinates, we're only telling you slope values. And then same over here. Does it matter that I didn't turn around? It's still leveled off for an instance, right? So this would be slope 0. Yes?
So could technically a horizontal line work as a solution as well?
So this is my lazy solution. Any horizontal line has slope 0 always, definitely has slope 0, those 3 points. If all we do is tell you slope values, you have lots of freedom. Right? So yes, if you drew a horizontal, hopefully you, I don't know, I already took your homework, so I'd say, just write in there, oh, my x-axis was also y equal 0. That was my real answer. As long as you drew axes, technically, as long as your x-axis was the graph, you're good. Any horizontal line would also satisfy this, right? There are infinitely many choices you can make that all work. As long as your slope is 0 at 3 points, we don't care. This one, it's easy to see, slope's always 0. All right. Any other questions on that problem? So far as this section, infinitely better than all of chapter 1. Other than the fact I already spoiled the surprise on Monday we do limits. But it's the only way to visualize or think about these in some sense. All right. Anybody want to ask questions on the homework or anything? I have some examples I could do real quickly, or 1 or 2 examples, or look at homework. Basically, all my examples are sketch a function where it has these slope values or these y coordinates at these points. So report. Couple ones I had in mind you can see right there. Okay, we can do these real quick. The homework kind of had two sets of things. There were three types of problems, if I remember correctly. One is, a lot of them look like this. And to me, this is the most important skill for now. Because what else is in this section? The other part is, here's a graph of f. Try to graph f prime. So, actually, we'll do that. I just want to talk about general strategy. If we have a problem like here is f, sketch f prime, how can we break that apart?
Figure out where its slope is horizontal and they've got the x-intercepts.
When is slope equal to 0? There and kind of starting here. So let's call this x value 1, x value 3. You know how we did this whole thing? There's only a couple examples where it was find where f of x is positive or negative. And what did we do? We drew a number line and we said, hey, it's 0 or undefined here. On this interval it must be positive, on this interval it must be negative. That's the main idea. We're going to do this a lot in chapter 3, which is why it's de-emphasized a little bit now. Which is why I was saying these are the more important types of problems, thinking like towards a test or quiz or anything. But this strategy we're going to use a lot going forward. At 1, my slope is 0. At 3, my slope is 0, and it seems to be 0 whenever I move past that. Right? This became horizontal. So then, what happens between negative infinity and 1? Is my slope positive or negative? My graph is moving upwards, so I'd say it's positive. What about from 1 to 3? Yeah, negative. All right. So then, what can f prime look like? It must cross the x-axis at 1, at 3, it's always 0. Then what happens in between? Left of x equal 1, it must be a positive number. Did anything crazy happen going from like negative to positive, or positive to negative? The graph just leveled off, right? Like I didn't say, here's a corner where it goes jump down to negative. I didn't have a shape like this, where the slope's positive and then negative. It was a smooth transition, right? So that means coming from 0 just moves this way. But I don't jump from here down to here. What happens after this? It gets more negative and goes back to 0. My slope is near 0, getting a little bit more negative. Eventually it's getting less negative because it has to go back to 0. So it just goes down here, turns around, comes back. Is this a valid guess for what f prime of x looks like? Does it have all the right properties coming from this picture? All right. General strategy is figure out when is my slope positive, when is it negative. Now I can draw that. My graph must be a positive number, my graph must be a negative number, must be 0 here, must be 0 over there. And that is pretty much all the detail you need. So that's if I'm going from f prime, or f to f prime. What about the other one? I'm given here's the graph of f prime. This is all the detail I usually do. Why did I label my number line f prime? I'm describing when it's positive and negative. I did the same thing over there. So when is it? It's roughly 0 and -1. After that, it's negative. On this side, oh wait, that's for slope. If this is the graph of f prime, what happens? Sorry, I was answering the other question. It's 0 here and here. At my x-intercept. So say this is the graph of f prime. When is f prime 0? At my x-intercept, true? What happens in between? It's positive. So what would f have to do? It would have to be decreasing, moving downwards because it has to have negative slope, and then level off, and then move to increasing because it's positive slope. Get to here, level off, and then go back down, right? Usually what I do is I say my graph does this shape. So ignore this part. If my slope is negative, then positive, then negative, my graph must do something like this. So now I just glue those together. My graph must do something like this. And when would this happen? This would be at x equal -4. This would be at x equal +4. Does it matter that I drew it above the y-axis or x-axis? What if I took that whole graph and moved it down? Yeah, change the slopes. I don't know any y coordinates, so it doesn't matter. So when I look at f prime, what's the important thing about f prime? It's decreased, or it's slope negative, slope positive, slope negative. Here's a graph that does that. It's backwards. Negative, positive, negative. I'm guessing that's why hands are raised. Slope negative, slope positive, slope negative, 0 at the 2 points that matter. Alright, so this could be a potential graph for f. Don't worry about fine details, just figure out positive versus negative versus 0. Anywhere you have a corner, and f would be a jump discontinuity in f prime. Alright, make sure y'all are working on the homework. Remember that's due Sunday night. And we'll start 2.2 on Monday, which is really just more of this definition.